Well, hello. Today we are going to be learning about graphing rational functions, and this is the first part of lesson 7.2. You're going to do two different evenings of 7.2 problems, and you can see there's a comic here where the number 8 is saying, "Don't you think you guys should stop fighting? You're both being irrational." And he's saying that to the number pi as well as the square root of 2. And that is because both pi and square root of 2 are called irrational numbers. They cannot be written as ratios. So if you see in the word rational, there is the word ratio. And so 8 is a rational number because it can be written as a ratio, such as 8 over 1 or 16 over 2 or any variety of other things. You know, there's lots of ways to write 8, okay? But they are all ratios of integers, of whole numbers. So when we're talking about rational functions, we're talking about functions that are ratios. So they'll be something like 2x minus 1 over x plus 5. A ratio of, well, ratio of what? These two pieces are polynomials. So if you have a ratio of polynomials, that's what's called a rational function. All right, so here is a picture that's taken from your textbook, and it's talking about what we would consider to be the parent function of a lot of rational functions. So when we talked about parabolas earlier this year, we had the function y equals x squared. When we talked about square root or radical functions, we had y equals square root of x and y equals cube root of x as our parent functions. A parent function for many rational functions is this one. Rational because it is a ratio of 1 and x. 1 is technically a polynomial, x is a polynomial. So this is my basic rational function, and it has some nice attributes, which are the asymptotes. So asymptotes are sort of like structural lines that the curve works around, so to speak. So you can see here that the two asymptotes for this function occur on the axes, actually, at x equals 0 and at y equals 0. The vertical asymptote occurs because the denominator cannot be 0. We can't do 1 divided by 0. That is mathematically undefined, illegal, impossible. So there is no graph at the location of x equals 0, so that vertical boundary is there because the graph splits or breaks at that point. And then the horizontal asymptote, we're going to talk about a lot, especially in the second video for this lesson, but it has to do with looking at the ratio of what we would call leading coefficients. For now, I think it's enough for us just to say that 1 over x has these two boundary or like structural lines that the curve works around. I think of them like scaffolding, right? Scaffolding kind of holds things up, and so these asymptotes sort of hold the curves in place on the coordinate plane. And then to find more points all along these curves so we know where to draw them, we could make any little table that we wanted, an XY chart. And this is my equation, y equals 1 over x. So I could put in different numbers for x and find out the y values and plot some dots, okay? And then I know that I would not go across that vertical asymptote in particular. So it's like a boundary. All right, so here is our first graphing problem. It asks me to graph the function 4 over x and compare it to 1 over x. So to graph 4 over x, I'm going to start out with just making a chart and also with thinking about asymptotes. So for asymptotes, I'm going to think, well, this graph is a lot like this one. This function has asymptotes at x equals 0 and at y equals 0. The only thing that's changed is the 1 has changed to a 4. So think about what kind of transformation that is. Function g is going to be 4 times as tall, to be like stretched out from the x-axis, as compared to f. And so those asymptotes are not going to be moved by a stretch out from the x-axis. The points on the x-axis will stay where they are, and then the points above and below that would stretch out. And then again, because you can't divide by 0, we can't have an x value of 0. So I'm going to have those lines as scaffolding. And then I'm going to think about different things I could plug in for x that would be sort of nice. For example, 4. If I have 4 over 4, I get 1. Or 2. 2 would be nice. 4 over 2 is 2. And 1 would be nice. 4 over 1 is 4. All right, so I'm going to just pick some numbers that are nice. Notice I didn't pick the 3. 4 over 3, I don't want to graph 4/3. No, I don't want to do that. So this is one that I did ahead of time just to save a little time. You can see I put some points in the chart, and I actually plotted even more than that. I did a few in my head. And then it asks us to compare this graph with 1 over x. So for this, let's take a look at a calculator. Okay, so I've got 4 over x and I've got 1 over x. And so 4 over x is going to graph in blue on my calculator, and 1 over x is going to graph in red. And you can see them here. And you can see that stretch that I was talking about, right? The blue graph is 4 times as tall at any one given value of x. The y coordinate is 4 times further out from the x-axis than it was on the red graph. Okay, so that's the kind of understanding we'd expect that you could have. I certainly could plot that also on this grid. I felt like it just got a little bit too cluttered, so I thought I would just show you on my calculator. Okay, here's one for you to try. I'd like you to pause the video and try this yourself. So as a little hint, we're going to start out thinking about our scaffolding. The only thing that has changed from the parent graph to this graph is the -6. So if I'm multiplying by -6, that's going to stretch things out, but there's also something else because of the negative. So let's think about that, right? 1 over x, that parent graph looks like this. I had 2 pieces with the asymptotes in here. Okay, so think about what that shape is going to end up being. Think about where the asymptotes are going to be. Plot some points. And then I invite you to come back in a little bit after you've tried it yourself and see how you did. So please pause. Don't just keep listening. Okay, so here's our picture. My picture is just the graph of g of x. Okay, I did not do both of them. So here is -6 over x. You can see that I took the asymptotes from the parent function. The parent function, by the way, is called a hyperbola. This 2-branch shape is called a hyperbola. I didn't remember to say that at the start. But just it's sort of like the word parabola, I think, because it says bola at the end. But that's the name of the shape. Okay, should that come up in your life somewhere? And so it's a shape that has these 2 like curvy pieces, okay? And then those 2 curvy pieces are separated by some asymptotes. So the multiplying by -6 isn't going to move those asymptotes at all, okay? So you still have those boundary lines that are on the axes, and then you can just plot some dots. It asked you to compare those 2, so let's look at my calculator again. So on my calculator, -6 over x is in blue, and the parent function is in red. So you can see the parent function in red is in quadrants 1 and 3. Why did this graph end up in 2 and 4 in the other quadrants? Well, it has to do with that negative, right? So the 6 is going to make things be 6 times as far out from the x-axis, but then this part that's down below is going to flip. Ooh, I didn't know that would happen. This part down below would flip up above. I guess I just did it again. All right, so the red part at the bottom would flip up to the top, and the red part on the top would flip to the bottom, because a negative is going to reverse top and bottom, right? It's a reflection over the x-axis. All right, so speaking of reflections and transformations and stuff, sometimes you have your parent function and it's written in a very nice form for you to see slides, okay? So just like normal, if I have some number that is with the x, that's going to move my graph side to side, okay? And subtracting by a positive x, like say this was x minus 4, that's going to move 4 to the right. And then this plus k, right? If I had a number out there like, so say I had 2 over x minus 4 plus 3. This 3 is going to be translating the graph up 3. And that translation up 3 is going to move the horizontal asymptote, just like this slide at the bottom is going to move the vertical asymptote. Okay, so the hyperbola gets slid around just like any other graph that we've done all year long. Okay, so let's take a look at this one. And I'm going to think first of all about where that scaffolding goes, where those asymptotes go. So I look at the bottom here, and x plus 2, if I have a plus 2 with the x, that's going to move the graph 2 to the left. So my asymptote that usually would be right here is going to move 2 to the left and be over here. Okay, I'm going to erase that because that's actually not anything we need. Okay, so that part is 2 to the left. So some people might think about it as I need to set the bottom equal to 0 and solve for that. Okay, and that is a way to find the vertical asymptote. I think it's kind of nice to just think about, okay, if I have an adding 2 with an x, that moves me to the left. And so the asymptote moves to the left. I think that's a little easier maybe. I don't know. Either way, it comes out the same. All right, and then the other part of my transformation is this minus 1. So normally I have a horizontal asymptote right here, but that is not going to be where it is because my entire graph is going to move down 1. And so that horizontal asymptote is going to lie at negative 1. Okay, so those 2 black dotted lines, that's my scaffolding. All right, and then I know that because the shape is going to be a hyperbola, I either have to have curve in the upper right and the lower left, right? So I either are going to end up with graph up here and graph down here, or the opposite of that. Whoops. Or, getting a little carried away here. I don't know what I'm just doing wrong here. Or if it's not those 2 sections, then my graph would be over in this section and over in this section. Okay, so it's one or the other because I know the shape has to be a hyperbola because that's the parent function. Now, if I'm not sure which of those, I can always rely on just plugging in some points. So I could make myself a chart and then just put in some nice numbers. So for instance, 2 would work swimmingly because 2 plus 2 is 4. And I'd have negative 4 over 4 minus 1. So that's negative 1 minus 1, which is negative 2. So if I just plot that, let's see where that is. 2, negative 2. Ooh, it's looking like it's the down in the lower right and up in the upper left. I think it's that one. Okay, so I invite you to pause the video, find some more ordered pairs here, plot them, and then we will compare answers in a second. Please pause. Okay, so your graph should look something along this line. We're not going to be super fussy about precision here, but we do want you to have the correct asymptotes marked. So my VA stands for vertical asymptote. That's the up and down line. The horizontal asymptote is the cross line. I want to write down where those are. Vertical lines are x equals a number. Horizontal lines are y equals a number. So I should write those as equations. And then I should plot enough dots that I can see where the 2 curves are. Okay, so if I needed to describe what had happened to this graph as compared to the parent function 1 over x, I would mention that there are several different changes. One of the changes is that the graph moved 2 to the left because of that 2. One of the changes is the graph moved 1 down because of the minus 1. And then the other changes are encapsulated in that negative 4. So the negative caused a reflection and the 4 caused a vertical stretch. Okay, these are all ideas we've seen with other graphs, just trying to reinforce that. Okay, the last thing that I have for you to do is to do a little calculator work. So for each of these problems, I don't want you to necessarily spend time like really making a fancy graph like we did on the others. Just a little doodle graph would be adequate. Right, so just draw like a little and then draw yourself, a couple little asymptotes, a couple quick curves, like wherever they are. Use your calculator. Okay, so put this in your y equals, look at zoom standard, look at what you see. Okay, the calculator is not going to show you the asymptotes necessarily. So make sure that you think about, okay, where should the asymptotes for this graph be? So for instance, in number 4, I would say, well, that -2 is going to move it down 2. So I know I have a horizontal asymptote at -2. And then this is x, just plain x. So there's still a problem when x equals 0. Okay, so I know I have those asymptotes. I look at my calculator, see what I see, and I could sketch in the curves. Okay, just real quick. Quick, sloppy work. Okay, just like not precision. All right, so graph asymptotes, graph what you see on your calculator. And then the key idea of this, like what I actually want you to practice for sure, is stating domain and range. So look at your graph and then say, what can x equal? What can y equal? You know, I think I actually should probably just finish number 4. Let's do that. Improvising a little. Okay, so I know that I have a graph. When I look at my calculator, it would look like this and like this. Kind of looks weird because it's chopped off there. Okay, the blue lines are the axes. The green lines are the asymptotes, and the red part is the graph. So if you look from side to side for the domain, there's a break in the graph at 0. So I know my domain would be from -infinity up to 0, break at 0, and then after 0, keep going. And for the range, I want to think about in the y direction. So if I look up and down, the place where there's a break in the graph is right here at -2 because of that asymptote. So I'm going to have a range of -infinity up till I get to -2. Then after -2, the y in the y direction, I still have more graph after that going up. So you could just notice that the asymptotes are where the domain and the range break. Okay? I'm sorry, I took over one of your practice questions. I would like you to go and graph on your calculator number 5 and number 6, draw a quick little doodle sketch, tell me the domain and range. Okay, I want you to pause the video, try them both. That's how you get the practice to do well. Okay, and then come back in a minute when you are ready to check. Okay, here are your last 2 answers. For number 5, there is a break in the domain at -4, because if I put -4 in for x, I'd be dividing by 0. So my vertical asymptote exists at -4. My horizontal asymptote hasn't moved as compared to the parent function, so it's still a break on the x-axis or at 0. For number 6, the problem in the domain, the problem value would be if x were equal to 1. I put in a 1 for x, I'm going to be dividing by 0, and that is not allowed. So I have a break in my domain at 1, and then this 5 has moved the parent graph up 5 units, and so that's where my new horizontal asymptote is. That is the break in the range. Right, I hope this went well for you. Please practice through doing the problem set today, and be in touch with your teacher if you do have questions. Thanks.